Hello everyone, and welcome to my home, which is on the traditional land of the people of the Eora Nation, and I would like to acknowledge the elders past, present and emerging. Today, I would like to tell you about how we're using serverless in order to fight COVID-19. I think this is not only exciting from a personal perspective, but also from an IT perspective, because here I think technology has become as vital as the healthcare workers themselves. And we've seen this firsthand by being Australia's largest digital health initiative, delivering across the full value chain from basic research, for example genomics, all the way up to delivering services to the healthcare system that really make a difference. Specifically, we are involved in Australia's response to COVID in a number of areas, ranging from research to delivering healthcare services. The one I'm going to talk to you about today is how we analyzed the virus genome to inform vaccine testing. But we also created the COVID dashboard, which informs governments to make public health decisions. All of this is powered by the data modeling work around health service utilization. We also delivered mobile health and telehealth technologies so that people don't have to come in person in order to see their healthcare provider. So with this, I want to talk to you about 3 areas. The first one is around monitoring, so to really understand what that disease actually is. To diagnosis, determine whether someone has coronavirus or something else. To tracking, of identifying the most vulnerable people and preventing them from contracting the virus. Now, this is no biology or public health talk. Therefore, we are going to talk about the actual cloud architecture that enable all of this to happen. But let's start by looking at what the virus actually is. So the disease is called COVID-19, but it's caused by the virus SARS-CoV-2, which is an RNA virus. In fact, it's a coronavirus that has 30,000 bases in its building plan. It is not a living thing. In fact, it actually has to infect your cells in order to reproduce. And it does that by connecting to the cell, by binding to a receptor there, injecting its genetic material, and then hijacking the cell's reproductive system in order to produce copies of itself that then pop out and burst out and infect other cells of that organism and of course other people as well. So with that, what can we do in order to fight something that we can't see and that is so unknown or so new? Well, we need to develop novel technologies, novel tools to really do the diagnosis properly, to do the therapeutics properly, to know how to treat it, and ultimately develop a vaccine that prevents the virus from spreading from person to person. Now, CSIRO is actually involved in the vaccine research, specifically at the Center for Disease Preparedness down in Geelong, where the virus is inside its high containment facility in order to produce a valid vaccine. Ultimately, once these tests have been done, they go to clinical trials, so testing in people, and then eventually it will be rolled out to the general public in order to prevent the disease from spreading. Now, what really makes this complex is that this blueprint of the virus is not static. In fact, it is mutating, it's evolving, and that's nothing sinister. That's basically what every virus or every organism is doing. The good news is that the coronavirus is mutating slower than other viruses. So for example, the influenza virus, where every year we need a new vaccine, is evolving much faster. It has accumulating more mutation faster compared to coronavirus. So my analogy is when you bake. You cut out the cookies and you basically have 2 choices. Either you use a knife and you roughly cut the shape, and this is basically what the influenza virus is doing. 6 arms, that's fine. It still looks like a star. But the coronavirus is a bit more precise. It's using a cookie cutter in order to copy itself and therefore have the same copy over and over and over again. So if there is a change in there, if a bit of dough is stuck in the corner, it is a small change compared to the different shapes of the star that might come out with the influenza virus. So with this, it is actually relevant to identify which strain or which isolate to use specifically in order to do the vaccine testing, because the wrong choice might be problematic. So stepping back a little bit and looking at where the virus has come from. So there's international agreement that it probably has originated from a bat. It might have had an intermediate host before it jumped to humans. As it jumps from human to human, it might accumulate these mutations, these adjustment to its new host, its new environment. There's currently discussion whether a specific version of the virus, a specific mutation called D614G, is more infectious than others, so could infect more individuals. Similarly, there might be a strain or a version of the virus that is more virulent, so can cause more severe disease. And this is basically where the monitoring comes in. We do need to understand how this virus actually functions, and the best clue is to look at its blueprint, its genome. And specifically, we developed a methodology that basically takes a fingerprint of the virus genome, that uniquely identifies it and can distinguish it from other isolates of the virus. And with this, we can then compare two or more of those isolates and understand how they relate to each other. In fact, we're using machine learning in order to map them on a 2D landscape to really visualize how far apart they are in evolutionary space from each other. So we've done this to look at the internationally chosen isolates for vaccine development and looked where they fall onto the landscape. And the good news is that they really well represent the current versions of the virus that are in circulation. So therefore, they are very accurate in representing the disease or the spread of the disease that is currently active out there. When I say they do that currently, we do need to keep on monitoring, because just because it matched today doesn't mean that it's still relevant in a couple of months or years down the track. So we've developed a web page that continuously ingests all the submitted data, all the isolates that are sequenced around the world, and looks at them and compares them to each other. So as you can see, it's a very basic version of the web page. So it would be great with, if people with UX experience would want to join the team in order to spruce this up a little bit. So in order to achieve this continuous analysis and a nightly build, we put it up on AWS. It's a semi-serverless workflow, as in there are still EC2 instances hidden in there, but they're triggered by Lambda, so I think that it still passes the test for this venue. Specifically, there's a Lambda function that monitors all the data streams that are coming from a database called DIS8, which holds the largest volume of genetic data on the virus currently, and is continuously fed with international viruses that are submitted to it. So this Lambda function sits there, monitors, and whenever there's a new version submitted, it kicks off the process of the rest of the pipeline, which is triggering a batch, so downloading that version and triggering a batch processing that spins up an EC2 instance, processes all the information of that version compared to all the other versions, and then updates the volume or the information on the web page for the user to see. Now, the reason we still need EC2 instance in there is because of the 30,000 bases that the virus is. It is not trivial to actually process the data, and therefore we have not gone down the parallelization route that you will see in the rest of the architectures. So therefore, this one is not completely serverless. So moving on to the next one, which is around diagnostics. Here, the next version or the next generation of these diagnostics are lab-free. So they do need to have the traditional approach of taking a sample and shipping it into a big pathology lab. In fact, they are meant to be a handheld device that can take a sample, be that blood or saliva, or sputum in order to analyze that and then say, ping, yes, no, you have coronavirus or not. Now, there are two competitors in the market at the moment. One is Sherlock and the other one is Mammoth Biosciences. And both of them use CRISPR technology in order to deliver this lab-free hands-on device. So, what is a CRISPR? A CRISPR is basically a protein that goes into the genome of the virus at a specific location and can identify whether that pattern that it sees there is coronavirus specific or is something else. The beauty of this approach is that it's actually programmable, which means that the components that guide the CRISPR to a specific location in a coronavirus can be exchanged to other, so identifying other viruses, or in fact identify specific isolates, so specific version of that virus. For example, in the future, if there is one version that is more infectious or one version that is more pathogenic, a CRISPR could be programmed in order to identify it and differentiate those. And this is exactly the technology that we developed, which is called Sorte. Sorte is able to identify the perfect programmable element, the perfect recognition site, in order to identify and differentiate specific version of the virus. Now, the webpage is fairly simple in that it lists all the potential programmable elements to it and basic statistics of how often was it found in coronavirus, how often was it found in other sequences, and therefore the researcher can then make the decision which one to actually go for. Again, as you can see, it's super basic. UX developers, please help us. All our effort went into developing the serverless architecture. And here, this is a true serverless architecture where you have the API gateway that handles the interaction with the user. From there, a Lambda function is submitted that handles the job, that in fact distributes the job, because we want to look at this particular coronavirus and all the other viruses. But again, as I said, the virus is quite large, so we want to divvy it up into chunks as well. And this is where the SNS topic comes in to fan out and collect the information back together from the Lambda function that looks at the off targets, so look at the targets, the off targets, and then collides all this information back together to be visualized on the web page. This brings me to the last section around tracking. So molecular tracking is basically the same thing, or tracing is basically the same thing as contact tracing, where you identify your central person that is infected and then backtrack to identify which other people might that person be in contact with. Now, rather than talking to people, here we can just look at the molecular signature of that individual and then identify who else has a similar signature and backtrack then where probably the infection pathway has happened. Now, what I'm showing here is the schematic of how it could be on a theoretical perspective. Now, this is how it looks like in real life. It is a bit more messy, but the idea is still the same, that you have the individual at the center that has contracted the virus, and then you backtrace and count the number of mutation or the number of genetic distances between that person and the next person, and therefore you draw the line if that distance is small enough to be probably the infection source. From this, to really go in deep and understand what we're actually seeing in this previous hairball, is we can distinct down and look at, for example, we pulled out this particular disease cluster where 3 isolates in New South Wales might have been infected by an individual from Victoria, or vice versa. So these these clusters actually are likely to be part of the infectious pathway. Similarly, we can identify unique mutations that identify a specific region. So we found this particular mutation that is active in Victoria and seen in 5% of the cases when we looked at the data in April, and is not seen in any other state, and internationally is quite rare as well. So this can then pinpoint specific location, which ultimately will help as well identifying where the origin is of maybe a new outbreak that is emerging. So for this, we developed a web page as well that enables people to track certain mutations in large cohorts, in fact in large distributed cohorts. And our use case was in India, where we do have multiple data sets that are distributed on multiple file servers, and we bring them in, do the analysis on top of those without having to download each individual and put them together in a database. And this, of course, was enabled by serverless technology as well. Now, as you can see, the architecture is quite similar to the previous architecture, therefore I'm not going to go through detail, but if you're interested, please get in touch. So another point that I want to raise is that in a post-COVID world, designing for resilience is much more important than designing for efficiency. And I think here, cloud, and specifically deployment at the speed of cloud, will really play into that, because by putting something on digital marketplaces, we can tap instantly into international markets, which of course is much more resilient and being limited to the market of individual countries. So what we've done here is basically develop a recipe, a deployment strategy that people can take off the shelf and deploy automatically in their account, which of course helps with data privacy as well, because in a typical SaaS model, you would have to ship off your data to someone else's account, have it processed there and get the results back. Whereas here, it's the other way around. You bring the analysis part in your account, analyze everything in the secure environment of your account and have the results there. So you're basically the driver of this. So here we've done that with Variant Spark. So Variant Spark is now on the AWS marketplace. And in fact, CSIRO has become the first public sector organization to actually have done that in the health space, which really attests to how difficult it actually is for a public sector organization to think through and adopt these new market channels. The only downside for this is that all of this is not available for serverless. Now, as a community, we definitely need to look into that, because in my mind, this is the distribution channel of the future, and therefore our serverless technologies, we want to market through the marketplace as well. So what are the 3 things to remember from the talk? I think there's a lot of IT tech that really has substantially helped in the fight against COVID. So I think every one of us can be proud of our direct or indirect contribution to this fight. So specifically, serverless has helped to overcome the unique issue of the coronavirus crisis, be that around extremely spiky workloads to privacy and data ownership issues that need to be overcome by distributed data resources. And marketplace deployment really play into the resilience that Gartner is calling for. So I'm hoping that as a serverless community, we can convince everyone that a serverless marketplace is truly needed. With that, thank you very much, and I would like to acknowledge my fantastic team. We are, as always, open for collaboration and grateful to accept help from community volunteers. If you want to find out more about the research we do and the tech we develop, please go to our webpage, bioinformatics.csiro.au. There, we do have a blog where we discuss our current affairs in science, of course, as well as discuss our latest findings. We do accept guest posts as well. With that, let's work together to make Australia the healthiest nation by 2030. And I'm looking forward to your questions now.